Morning, doctor. Today we're going to discuss our CIFE for 40 second assignment. My name is Omar Noairi and my teammate is Ahmed Wardani. We will start briefly with an introduction and theory about open channels. Open channel hydraulics, uniform flow occurs when the velocity and depth remain constant with gravity and friction forces balanced. This idealized condition is found in long prismatic channels where the slopes of the water surface, the channel bottom, and the energy grade line are equal. The Manning formula is used to calculate discharge in the uniform flow with Q equal to Km over N times the area times the hydraulic radius to the power 2 over 3 times radical S0. Specific energy represents the total energy per unit weight of water, including flow depth and kinetic energy. It is expressed as E, with energy, equal to Y plus V squared over 2G. It helps identify flow behavior, such as determining critical depth, whether it's subcritical flow, which has a higher depth and a lower velocity, and supercritical flow, which has a lower depth and a higher velocity. A specific energy curve plots the specific energy against flow depth, showing whether the flow is subcritical or supercritical by comparing the actual flow depth to the critical depth YC, where the Froude number is 1. So this is the problem that we have created. It starts off with a water flowing in a long triangular channel with a slope equal to 1% and equal to 0.014, whereby it passes by a downstep. After, it undergoes a hydraulic jump before reaching a Cipollati weir with a L equal to 1.68 meters, P equal to 1 meter, CD equal to 0.63, and with a side slope of 1 vertical corresponding to 4 in the horizontal. The reach between the weir and the upstep is long and rectangular. The depth downstream of the weir is Y3 equal to 3 meters. So the first, we decided to do 3 questions. The first being to determine whether the water surface level rises or drops on the downstep without using any calculations based on the theory. The second question is that given that the depth of the triangular channel, it maximizes flow for a fixed area, find the depth Y1 in the channel given that Y2 equal to 5 meters. The third and final question is to find the delta Z critical for the upstep downstream of the weir, given that the energy E, which will be plotted on the x-axis, versus the water depth Y, which will be plotted on the y-axis, plot is given below.
Okay, now we're going to be starting with the solution to the problem. So the first problem asks us whether the water surface drops or rises on the downstep. So we know that a hydraulic jump occurs after the downstep, which means that the flow after the downstep and before the jump is supercritical, and after the jump is obviously subcritical. Knowing that upsteps and downsteps don't change the flow regime, that would mean that the flow at the downstep is the same as after it, which would mean that it is supercritical, sorry. Hence, the water surface level drops during the downstep. Okay, now we're going to be solving for Y1, the question 2, Y1, the depth here, Y1. So we're going to first consider the triangle below. It has the ratio vertical to horizontal is 1 in the vertical and to m in the horizontal, but this m is unknown. However, we are given that the flow is maximized for the area of the triangle. Hence, we need to minimize the wetted perimeter, as flow and wetted perimeter are inversely proportional for a fixed area, and this is known from Manning's formula, since the perimeter is in the denominator, and as we decrease the denominator, the number is going to be bigger, the flow Q. Okay, so the area of the triangle that we just showed is going to be my times y over 2 times 2. So base times height over 2 times 2, because we have 2 triangles, we can divide them, which will give my squared. And this value has to be fixed, which means that dA over dy is equal to 0, i.e. like a is a constant deriving with respect to y. Now, the wetted perimeter P, it's equal to 2 times the square root of y squared plus my squared. And after simplification and writing m in terms of a and y, which would be a over y squared, we get that the perimeter is 2 multiplied by the square root of y squared plus a squared over y squared. So to minimize p, we're going to set dp over dy equals 0 as the minimum of a function, which implies that 2 multiplied by the derivative is equal to 0. Now, we just need the numerator equal to 0 to solve. So that would mean y power 4 equals a squared, which is equal to m squared times y power 4. So y power 4 equals m squared times y power 4. Hence, m is going to be equal to 1. The channel area is y at that section is y1 squared, and the wetted perimeter is 2 times radical 2y1 squared at y1, of course.
Okay, so now we need to find y1, which is the point of the question. So we first need to find q using the Chipoletti-Weir equation, which is q equal to 2 over 3 CD L minus 0.1 times n times h times radical 2g times h power 3 over 2 plus 8 over 15 times CD times radical 2g times tan theta over 2 times h power 5 over 2. CD is given equal to 0.63. N in our case here is going to be equal to 2. To find H, we need to subtract the total depth above the weir minus the height of the weir, which is P. So we get 5 minus 1 equal to 4 meters. We have that L equal to 1.68 from the given. And in a Chipoletti weir, we know that tan theta over 2 equal to 1 over 4, equal to 0.25. Plugging in the values into the equation, we will get that Q equal to 25 meter cube per second. So now we use the Manning's equation to solve for y1. We express the area in terms of y1 and the hydraulic radius as well in terms of y1. And then we solve for it and we obtain that y1 equal to 2.074 meters.
Okay. So now we're going to be moving on to the third question, which is finding okay. So now we're going to be moving on to the third question, which is finding delta Z critical of the upstep that is downstream of the weir. So we are given this plot, and we can find YC from it. So as we can see, so YC is going to be at the minimum E, when E is minimum. The depth at that point is YC. So as we can see from the graph, it's going to be around 2.5, hence YC is 2.5. And now we're going to continue. So we have the reach between the downstep and the weir is rectangular, hence YC is equal to the cubic root of Q squared over G, which gives that small q is 12.38 meter cube per meter second. Now we can find the width B using Q, big Q divided by small q. So we get that it's 2.02 meters. And finally, to find delta Z critical, we're going to write the energy equation between 0.3 and 0.4, where 0.3 is the point before the upstep and 0.4 is on the upstep. And we're going to have to be using YC for Y4 and delta Z for delta Z. And now we find the velocities using the volume flow rate or continuity equations, which is just flow divided by area. And we get the velocities and we plug in the values, as we can see here, and we just subtract the heads at 3 minus the heads at 4, and we're going to get delta Z critical, which is equal to 0.118 meters or 11.8 centimeters. So that was it, and thank you.